Let me introduce you to Evangelista Torricelli, an Italian physicist who unfortunately passed away at the young age of 39 from typhoid fever, but not before he gifted the world with a very well-known invention. Evangelista Torricelli was the inventor of the barometer. You know that atmospheric pressure can be expressed in units of pascals. 1 atmosphere is the same thing as 1.01 times 10 to the 5th pascals. And you're probably also familiar with the way a barometer works. A simplified diagram of the barometer shows an inverted tube of mercury, and the weight of a column of mercury can be supported by the difference in pressure between the vacuum at the top and the atmosphere pushing down on the fluid from below. And the largest column, the greatest height that can be supported under normal atmospheric conditions, is 760 millimeters. And so this is why 760 millimeters of mercury is another way of saying 1 atmosphere of pressure, and it's not uncommon to refer to that as 760 torr. In other words, a torr is a pressure unit in honor of Evangelista Torricelli equal to a millimeter of mercury. We also have something known as Torricelli's theorem, which gives an equation that we can use to describe the speed with which fluids drain out of a vessel. So here we have a vessel with a large height, h, and a large diameter, d. Here's another vessel with the same height, but a smaller diameter, and yet another vessel with a smaller height and also the small diameter. So how does the height, the overall height of the vessel and the diameter factor into the speed with which the fluid drains out of some exit hole? Now, in all of these examples, consider that the vessel is open to the atmosphere at the top. If the top were sealed off and you puncture a hole here, the fluid wouldn't drain out at all, provided the height isn't so great that it exceeds 10 meters. After all, if this were sealed off instead of open, a vacuum would exist here, and then in the same manner in which a barometer can support a column of mercury, a vacuum can support a column of water, provided it's not too tall of a column of water. No. So we're going to consider all of these are open vessels at the top. So the question is, in which of the 4 cases, A, B, C, and D, is the velocity with which the water flows out of the exit hole the greatest? Go ahead, mark your guess somewhere on your paper. Did you say the same? That's right. In all 4 cases, the speed with which the water flows out of the hole would be the same. It doesn't depend on the total height of the vessel or the diameter. All it really depends on is this value y, the distance between the top of the vessel and the exit hole. Now we're going to assume here that the fluid had originally started all the way at the top, right? When it gets to the point where the fluid reaches the level of the exit hole, then the velocity goes to 0 at that point. So as the fluid drains and the level at the top goes lower and lower, then the velocity gets less and less until it finally reaches 0. So we can derive an equation that expresses how fast the fluid should flow out. And in fact, if the diameter of the vessel is really large in comparison to the diameter of the exit hole, then as the fluid's draining, you would barely perceive the drop in the fluid level. And so if this diameter is much, much greater than the diameter of the exit hole, then the level barely drops, and the value of y is nearly constant. And then the exit speed would remain a nearly constant value. So how can we solve for that exit speed? Well, we can start by expressing Bernoulli's equation. The pressure at, we'll say, point number 1, let's imagine it like this. As it drains, some amount of fluid that started here has to make its way out here and become the fluid that came through the exit hole. So we have a point number 1 and a point number 2. The pressure at point 1 plus rho gy1 plus 1/2 rho v1 squared equals pressure 2 plus rho gy2 plus 1/2 rho v2 squared. Hopefully you recognize that as Bernoulli's equation. Well, if the top is open to the atmosphere and we've punctured a hole that also opens point 2 to the atmosphere, then both pressure 1 and pressure 2 are the same. They're both just 1 atm. So we can cancel that out from both sides of the equation. If we're clever in our choice of reference level, then we can say the exit hole is the place where height is equal to 0. So that allows us to cross out, that allows us to cross out rho g y number 2. So now we're left with rho g, and then there's no need to put the subscript number 1. Y number 1 is this value, y. So rho gy plus 1/2 rho v1 squared is equal to 1/2 rho v2 squared. But what is the velocity here at point 1? Well, the water here at the top, if this diameter really is much, much greater than the exit hole, the fluid near the top is nearly static. And so the velocity at point 1 is 0. So that term goes away. Now that allows us to cancel out the rho on both sides of the equation, multiply both sides of the equation by 2, and we have v squared is equal to 2gy. Oh, look at the result we're getting. V is the square root of 2gy. We've seen this time and time again in our study of physics, especially in cases where gravitational potential energy is converted into kinetic energy. And you can see a draining vessel essentially is that same situation. The water starts out up high, loses gravitational potential energy as it comes out of the exit hole, and converts that into kinetic energy. So this is Torricelli's theorem. And it's nice to see that it agrees with our concept of law of conservation of energy. Kind of fun example of applying the way in which fluids drain out of containers, and an example of Torricelli's theorem can be seen in a Spanish porron, which is a vessel I think that was developed in the Catalonia region of Spain, and typically is used as a way to pour wine. The only time I've ever used a porron was in a Spanish tapas restaurant in Asheville, North Carolina. I've been to Spain and I've been to the Catalonia region, but it turns out the one time I've used a porron was in North Carolina. Here's a picture of yours truly pouring some wine into my brother-in-law's mouth. This was after a lot of practice. On the first attempt, it's pretty typical for the wine to spill all over the place. It takes a little practice before you can actually aim it properly. So let's move on. Let's see another question we can ask about draining vessels. How about this one? What if I have a container and it's draining in accordance with Torricelli's theorem? I put a hole here. Hey, wait a minute. Let's backtrack. What if I had two containers? Everything seems the same. They're both filled to the top. The tops on both of them are open to the atmosphere. The depth of the hole that the fluid flows out of, y, is the same for both vessels, but the exit hole is greater in case number 2 than it is in case number 1. Then does it flow out faster? Well, it depends on what your idea of faster is. If faster to you means v, the velocity, then no, there's no difference in the speed. However, as far as the rate, yeah, it would drain at a faster rate in case number 2. That's because flow rate is measured in cubic meters per second, and the area of this exit hole, A2, is greater than the cross-sectional area of exit hole A number 1, and isn't flow rate found by multiplying area times velocity? So sure, vessel number 2 would drain with a greater flow rate, but the speed with which the fluid comes out would be the same in both cases. In other words, the speed of the fluid is not a function of the area of the hole. The flow rate is, the speed is not. The speed is only a function of the value y. V is the square root of 2gy according to Torricelli's theorem. So, here's the question I want to get to. How would you maximize the range of the projectile motion for the draining water? So should I put the hole up high at point 1, somewhere near the middle at point 2, or somewhere down low at point 3 if my goal is to get the water to land as far away as possible? I want to maximize the distance where the water, or it doesn't have to be water, whatever the fluid is, I want to maximize the distance where the fluid lands on the tabletop. So we're trying to maximize the range, and as you know, the range is just the horizontal velocity multiplied by the time of flight. And by the way, this would be an example of a projectile following exactly half a parabolic trajectory. It's not a full parabola where it rises and falls, it's just this second half of the trajectory. And you probably know that the time spent in flight for those type of projectiles is equal to the square root of h over 2g, or I'm sorry, the square root of 2h over g. Remember where that comes from? Distance is equal to initial velocity times time plus 1/2 acceleration times time squared. But if you're following half parabola, the initial velocity, at least along the y-axis, is 0, so this term goes away. If we multiply both sides of the equation by 2 and replace a with g, then yeah, sure enough, we get t is the square root of 2h over g. So let's put these two together, and we can say range is equal to v times the square root of 2h over g. But then again, according to Torricelli's theorem, v should be the square root of 2gy. So we have the square root of 2gy times the square root of 2h over g. Let's make sure we understand what all these labels refer to. So here's the vessel, trying to figure out where to put the hole to maximize this range. As it drains out and hits the tabletop, there's the r in our equation. Is this h or is this y? Right, this is the y in the equation, and then this is the value of h in the equation. Okay, and we can also say that the total height of the vessel is maybe capital H. So if we move the hole to a different position, then not only have we changed the value of y, but we've also changed the value of little h, but capital H stays the same regardless. Capital H is just lowercase h plus y. So we can make a substitution and replace y with capital H minus lowercase h. So now we have range is equal to the square root of 2g times capital H minus lowercase h times the square root of 2h over g. We could put that all together under one square root symbol. If so, the g's will cancel out, and now we'll have the square root of 4h times h minus h. So we have range is equal to 2 times lowercase h, capital H, minus lowercase h squared all to the 1/2 power, in other words, square root of. And so if we want to maximize, how do we do this? Can't we always maximize a function by setting the derivative equal to 0? So if I want to find the ideal value of h that creates the maximum value of r, then we can set dr dh equal to 0. So what is dr dh? Dr dh would be equal to 1/2 times 2 lowercase h capital H minus lowercase h squared to the negative 1/2 times the derivative of all of this, which would give us capital H minus 2h. Okay, so if we want to set that equal to 0, then all we really need to do is set this term equal to 0. So if capital H minus 2h equals 0, then h is equal to h over 2. That's probably what you would have guessed anyway, right? If I said I'll give you the choice of these three, which one do you think leads to the greatest range? Right in the middle is the one that creates for the greatest range. Now, hole number 1 seems like maybe it would create for a great amount of range because, after all, the water that comes out of that hole is going to spend the greatest amount of time in the air, and with more time should come greater range. But then again, even though it spends more time in the air, it's coming out with a smaller velocity because Torricelli's theorem says the velocity is just a function of how far the hole is below the top of the vessel. So then you say, oh, okay, well, if the greatest speed comes from the greatest depth of the exit hole, then 3 should give the best case. That's going to create for the most speed. But at the same instant, then it's also creating for the least amount of time because it's not very high above the ground. So the best of both worlds is case number 2, as we just found in our derived work. So there's an introduction to Torricelli's theorem. Let's see where else it comes up in the rest of our lesson on fluid dynamics.